All right, welcome back to part two of this video where we're talking about moments and center of mass in Calculus 3. Okay, so just a quick reminder that in this section, whenever we talk about units, we're just gonna assume everything's globally in SI units. All right, so key terms. Lamina, remember, is going to be our notation for a very thin plate, which we think of this as a domain in the plane. All right, what do we have to do? So step one is to find the mass of the lamina bounded by the following inequalities. Okay, so I've got x squared plus y squared is less than or equal to 9, and I've got y is greater than or equal to the absolute value of x. They also tell us that the density is 2 times the square root of x squared plus y squared. Okay, so let's start with that information. Let's start with a picture. So we've got x and y plane right here. So of course, by now you should recognize x squared plus y squared less than or equal to 9 is a disk centered at the origin of radius, let's say 3. Let's not say, it is 3. Okay, and if we just take this piece of information into account, we know that this is inside of the disk. But we've got a second piece of information. Y is bigger than or equal to the absolute value of x. So what is that? As always, if you come across an unfamiliar inequality, we should start with the equality case. So y equals absolute value of x, I hope you remember from your pre-calc or calculus days, is the following V shape. Okay, so there's my labels here. Okay, well, since we want the y values above the absolute value of x, what that actually entails is shading this region above. So taking these two pieces together gives us the domain D, that's this cheese wedge over here. Make it a little bit darker. Okay, so getting rid of the intermediate shading. So this is the domain or the description of the lamina D. Okay, the other piece of information to take into account is that it's actually telling us that we've got some density. So here it's using delta as the density, that's fine. Now let's think about what this is telling us. It's just telling us it's 2 times the distance to the origin. So the further away our point is, the heavier it's getting. So just kind of visualize what that's happening here is imagine these kind of really thick lines means that the density is very, very strong. The further away from the origin that we get. And then of course, it gets way more light as we go towards the origin. So I don't know how to represent this well, but basically it gets thicker and thicker towards the outside. So it's heavier on the outside, lighter on the, or towards the origin, I should say. Okay, so without doing any calculations, first, actually, we'll come back to like the geometric center of mass in part B. For part A, we need to calculate the mass. So let's start with that. What is the mass? So let's just start off with how should you remember your formula? Double integral of your tiny bits of mass over, in this case, the domain of integration is this lamina. Okay, but what is mass? Mass is density times geometry. Density times geometry, in this case, is the density, delta, times area. Okay, so let's write out the actual density that they give us in this problem. So I'll set up the integral in a second, but for now, remember our density is 2 times the square root of x squared plus y squared. And our dA, we have to basically choose. So remember, we've got two choices, dx, dy, or polar coordinates. Now, given that we've got the square root of x squared plus y squared, and our domain D is really nice in polar coordinates. I would say that this integral is screaming for polar coordinates. So let's describe this in polar. Well, let's do thetas and r. What can we learn about our theta? Well, this angle over here, if that is the line y equals x, we hopefully remember in radians it's pi over 4. And the line over here is 3 pi over 4. Again, you can just kind of think about that by saying, okay, here's pi over 4, here's another pi over 4, and here's a third pi over 4. Okay, if you don't like that, of course, what I would encourage you to do is plug in some points. If you plug in the point 3, 3, I'm sorry, that's not 3, 3. Oh wait, it is 3, 3 because it's on the line y equals x. You can figure out what theta would be using arctangent is 1, which is pi over 4. And then here you'd get negative 3, positive 3. Actually, those aren't, I'm so sorry, those are not on that circle. So 3, 3 is actually up here. Minus 3, 3 is over here. Okay, long story short, those are our angles in radians. So we've got smaller angle is pi over 4, bigger angle is 3 pi over 4. Our radius is even simpler. What are the inequalities? Well, keep in mind we're allowing r go from all the way down to the origin, so r is 0 at our smaller limit, and then the biggest value of r we would allow would be 3. Okay, cool. So now that we've got that, time to set up our integral. So we've got integral 2 times, well, I suppose we should change our x squared plus y squared into polar. First thing is I like remembering x squared plus y squared is r squared. If I want the square root of that, well, that just picks up an r. So that's pretty handy. So we've got 2r, 2 times r, times. Now our dA, of course, in polar coordinates is r dr d theta. And let's put the r, let's put the d's with some spaces, and then let's think, is there any advantage to writing the integral in a specific order? We should always keep in mind what are the limits of integration. So of course, I hope you see that the limits of integration are constant in both theta and r. So Fubini's theorem tells us we can write them in any order that we like. So I'm just going to do thetas on the outside with r on the inside. R goes from 0 to 3. Okay, so there's our setup. So pretty nice. Let's calculate it. I would say another really lovely trick is in order. This is the trick called sometimes useful, which means when we've got an integrand where we've got functions that are products, we can split the integrals up into products. So we've got 2r squared dr is our integral in r, and d theta has no function, so it's just d theta. Okay, so pi over 4 to 3 pi over 4, 0 to 3. Let's integrate. So we've got theta, and theta goes from pi over 4 to 3 pi over 4 times 2/3 r to the third. R goes from 0 to 3. Okay, so 3 pi over 4 minus pi over 4 is our integral in theta, times 2 over 3, 3 to the 3, so 3 cubed, minus 2 over 3 times 0. Okay, almost done. Let's continue down here. So 3 pi over 4 minus pi over 4 is 2 pi over 4 times, and then let's see, actually, cancel the 3 out. I've got a 3 squared. What is that? That is 9 times 2 That's 18. Okay, couple simplifications here. 2 pi over 4 is 1/2, and then of course I can pull out 2, and I'll be left with 9 pi. Remember my disclaimer that, again, mass, we'll just use the SI units for mass. So we've got that 9 pi kilograms would be the mass of this lamina. Again, this lamina is kind of funky in that it gets thicker the further away that we go from the origin. All right, wonderful. So there's our mass. Next up is to calculate the center of mass. So this is more involved, and this is where we need our formulas over here. Okay, so before we do any calculations, let's kind of think through the geometry of this. Again, if you try to imagine a little fulcrum hiding underneath this object, where would you put it so that it perfectly balances? Because of the circular symmetry, I hope you see that it makes sense that probably the center of mass is going to be somewhere along this red line. That red line is x equals 0. And then where should the y coordinate be? Well, first of all, since this is a circle of radius 3, let me put 1, 2, and 3. Basically, because it's thicker as we get further away, I would say that the y value is going to be closer to the top than it is to the bottom. How much so, I'm not 100% sure. So, I'm going to just say somewhere over here is where we think the center of mass should be. So let's see how good our intuition is by now just using our formulas and calculating the center of mass precisely. So keep in mind, here are the formulas. We say x bar is the x coordinate of the point that is the center of mass. Y bar is the y coordinate of the point that is the center of mass. And we've got these formulas here where we've got the moments divided by the total mass. Okay, so let's jump right in. Let's start our calculations. So we've got, let's say, part B here. We need the center of mass. So we need x bar and y bar. Let's start with x bar. So to do x bar, I'll remind everybody it's my over m. We already have the total mass up here. This is our little m, or sorry, big M. So let's calculate our moment my. What is that? That is the double integral where we measure the distance of a tiny chunk of mass to the y-axis. So measuring to the y-axis, that's where the x comes in, and then I've got a little chunk of mass. Okay, so that is how I memorize the formula. Now let's set this up. So we've got x times our density times our little chunk of area over the domain D. So we calculated our first integral using polar coordinates. We should think about whether polar coordinates is still appropriate. Well, the domain still has that nice polar symmetry. We still have this in our integrand. So I think we should still use polar coordinates for this. So I would say this is screaming for polar just as much as the last integral. Let's also remember that x is equal to r cosine theta in polar coordinates. All right, let's jump in. So my then is double integral. Let's replace x with r cosine theta times 2 times, remember in the last section, or the last part, we had that the square root of x squared plus y squared just simplified to r. So I pick up an r from the density. And then we've got r dr d theta. Okay, and just like last time, the dr and the d theta, the order doesn't quite matter. So theta's on the outside, pi over 4 to 3 pi over 4, and then 0 to 3 for r's on the inside. So looking at the functions here, it's all multiplications, so we can use our other trick, or sometimes useful trick, to split this up as a product of cosine of theta d theta. This time, much more interesting function to integrate here. Notice that we do have a function in theta, cosine. So this is from pi over 4 to 3 pi over 4, times the integral in r, which I've got how many r's? Let's count. 1, 2, 3. So we've got 2r cubed dr. R goes from 0 to 3. Okay, let's crank this out. So the integral of cosine is sine. Theta goes from pi over 4 to 3 pi over 4 times 2/4. So that is 1/2 r to the 4th. R from 0 to 3. Okay, so now we need to evaluate sine. So again, you might have this memorized, but I always like to do everything visually. Here's a quick little unit circle. Pi over 4 is over here. 3 pi over 4 is over here. And if I just remind you here, notice that the y values are the same. And in this case, they happen to be root 2 over 2. But geometrically, we're going to get that sine at these two values is the same value. So we're going to end up getting 0 here. So again, root 2 over 2 minus root 2 over 2 times, doesn't really matter, but let's go ahead and calculate this. 1/2 3 to the 4th power minus 0. Okay, but of course, this ends up being 0. So we've got that our moment my is 0. Okay, so that tells us that x bar, which remember is my over m, is 0 over 9 pi. 9 pi was, yep, it was our mass in the first step. Okay, this tells us that x bar is 0. Since I said we should use SI units, I've got the little m for meters on the outside. Okay, good. Let's take a look at our picture. Does that agree with our intuition, right? Is the x coordinate of the center of mass at x equals 0? Looks like it. So far so good. This agrees with our intuition. So time to calculate our second coordinate. So those are our formulas. Here we go. Y bar is mx over m. What is that? Well, mx is, as a reminder, double integral over the lamina d. Mx is the distance to the x-axis, which is where the y comes in. And then, of course, we've got a little tiny chunk of mass, dm. Okay, let's set this up. We've got y times the density. Here's our density times dA. And just like last time, I think our integral is quite similar from the last part, except for instead of an x value right here, we've got a y value. But I think the similar process will be to, let's just run through the same steps, right? We've got that this integral is indeed screaming for polar coordinates. This time, let's remember y is r sine theta. Again, you should have these memorized. Okay, so let's set up our integrals. So r sine theta is our y value. 2 times r was, again, square root of x squared plus y squared. We've done twice now. That's just 2r. And now our dA is, again, I like putting parentheses here to kind of remind me where pieces match. R dr d theta. Again, I don't really need to, I don't need to worry too much about the The order, we've already done that thinking a couple times now, where 0 to 3 is r on the inside, and then pi over 4 to 3 pi over 4 on the outside. Okay, next trick is, of course, sometimes useful. Seems to work yet again. So let's split up our integrals in terms of theta first. Pi over 4 to 3 pi over 4. Now let's grab the functions with theta. Sine theta d theta is all we have, times 0 to 3. Let's group all the functions of r. So let's do 2r, how many r's? Cubed, just like last time, dr. Okay, so Nike method, just do it. We should know how to crank out integrals like this in our sleep. So integral of sine is negative cosine. Again, do a quick little guess and check. Derivative of cosine is negative sine, so I have that extra minus sign to counteract it. Okay, and carefully plug in our limits of integration. All right, integrating in r, so 2r to the fourth divided by 4. 2 over 4 simplifies to 1/2, but I've got 2r, 1/2 r to the fourth power. R goes from 0 to 3. Okay, almost done. So we've got negative cosine of 3 pi over 4 minus a negative, so that becomes plus cosine of pi over 4 times 1/2 3 to the fourth power minus 0. Okie dokie. So let's calculate. Let's draw a little tiny unit circle just to remind ourselves. Right? 1, 2, 3 whiskers. 1, 2, 3 whiskers. We are at pi over 4 and 3 pi over 4. However, this time, notice that at pi over 4, our x is positive. And at negative pi over 4, at 3 pi over 4, our x is negative. So keeping that in mind, and again, at pi over 4, cosine and sine are the same. They're root 2 over 2. So I'll pick up negative root 2 over 2 when I evaluate negative cosine at 3 pi over 4, plus root 2 over 2 by evaluating cosine at pi over 4. All right, and I suppose I have to evaluate 3 to the fourth power. That is 9 times 9, 81. All right, so I've got to keep calculating on my next page over here. So I've got 2 pi over 2 plus, I'm sorry, pi over, I can't talk. Square root of 2 over 2, there we go, plus square root of 2 over 2. So that's 2 square root of 2 over 2 times 81 over 2. So those end up canceling, but the others survive. So here we have it. 81 square root of 2 divided by 2. Now, what is that? That is not our final center of mass. That is just our moment about the x-axis. So that tells us that y bar is mx over m. So we've got 81 root 2 over 2 divided by 9 pi. Just double check, our mass was 9 pi. Okay, so let's simplify this a little bit. So I've got to do 81 divided by 9 is 9. So 9 root 2. And then the 2 pi doesn't really simplify. So I will leave it like this. Okay, keep in mind that y bar, the units of this would be a distance. So I like to put them outside. Is that the yeah, that's how I wrote it earlier. Okay, so let me grab my calculator and let's figure out what is 9 square root of 2 over 2 pi. So that's approximately 2.02. And let me make sure. Okay, I don't need to do it in radians. I mean, there's no trig functions here. Okay, so 2.02 is our y coordinate. Let's take a look at our picture here. So remember, we said in part, we already calculated x bar to be 0, which matches our intuition that the center of mass was along the line x equals 0. We got that. Now we know what the y value is. We've got x bar was 0 and y bar was about 2.02. Put squigglies. So remember that this was like about 2 right here. Here's 1, 2, and then 3. So pretty good. I don't know. I was just, sketching this, but it turns out my sketch was really, really accurate because, again, I was relying on intuition based off of the fact that the density was 2 times the square root of x squared plus y squared. So again, it was getting thicker the further away I was going, so that the center of mass was kind of gravitating towards the thicker part. All right, cool. So that wraps it up. All I'm going to do now is just write a nice little center of mass. Write this as ordered pairs. X bar, y bar equals 0, 9 root 2 over 2 pi. Put a box. Try again. Units are measured in meters. There you have it. Lovely problem over here. I hope you enjoyed that. So do a lot more of the ICAs here. See you in class.